Section 4.4, Adding and Subtracting Polynomials. We're not going to look at the graphing in this section, but we are going to need to know what is a polynomial. If we're going to be adding and subtracting them, we should know what they are. And later we'll be multiplying and dividing, and in Chapter 5 we'll be factoring. So here's the beginning of our study in polynomials. Toward the beginning of the section, second page, page 289, in the brown box, middle of the page, we define a polynomial in X. It says a polynomial in X is a term or the sum of a finite number of terms of the form ax to the n, where a is real and n is whole. A polynomial is a single term or the sum of a finite number of terms, finite meaning not infinite, all of those terms being of the form a times x to the nth power, where a is real and n is a whole number. So let's just look at some examples, and I want to ask the question, is this a polynomial? Let's say I've got 2x to the fourth plus 3x cubed plus 5x squared. Is that a polynomial? Well, it is a sum of a finite number of terms. It is the sum of three terms. And all of the terms look like ax to the n, where the coefficients are real and the powers are whole numbers. 2 is real, 4 is whole. 3 is real, 3 is a whole number. 5 is a real number, and 2 is whole. So yes, that is a polynomial. What about this? Do we have a polynomial? Is this the sum of a finite number of terms? Yes, it is. We can think of it that way. I know it's a difference. I know there's a subtraction there. But we think of this in terms of addition by thinking of this as plus a negative 7x to the eighth. And so I can consider this a term, knowing that that sign belongs to that term, that sign belongs to its coefficient. And each of these terms looks like ax to the n, where the coefficient is real and the power is whole. 6 is real, 5 is whole. What's the coefficient on this second term? The negative 7. Negative 7. Signs belong to their terms. Negative 7 is a real number, and this power 8 is a whole number. What about this guy? Is this a polynomial? It is the sum of a finite number of terms, two terms, and do they all look like ax to the n, where a is real and n is whole? And the answer is yes, they do, because of the things that you cannot see. What's the coefficient on this first term? Coefficient is 1. If there's just a single x by itself, what's the power on that x? That's x to the first. 1 is real, and this power 1, that's a whole number, so that works. What about this term? If there are no x's, how many factors of x are in this term? 0. So can't I write that this is 4 times x to the 0 power? X to the 0 is 1, and 4 times 1 is just itself. So there are a lot of 1's that you can't see. But in the final analysis, yes, x plus 4 is a polynomial because it's two terms, and in each term the coefficient, this 1 and that 4, are real numbers, and the powers, that 1 and that 0, are whole numbers. Is this a polynomial? Well, it's not a sum of terms, it's a single term. But look back at your definition. It said a polynomial in X is a term or the sum of a finite number of terms. Well, this is a term where the coefficient is real and that power is a whole number. What about 9? Is 9 a polynomial? Just sitting there by itself? Yes, it is. It is a term where the coefficient, that's the 9, is real, and the power on x, what's the power on x? Just like here. That's times x to the 0, and 0 is a whole number. So all of these are polynomials. What would not be a polynomial? Something like x squared plus 1 over x. The first term works, but this last term cannot be made to look like ax to the n, where a is real and n is whole. The coefficient is 1, but what's the power on that x? If I bring it to the numerator, isn't that a 1x to the negative 1? And negative 1, a power of negative 1 is not a whole number. So this is not a polynomial. What about square root of x minus 3? The minus 3 is fine, but the square root of x, it doesn't fit our format. So these would be examples of expressions that are not polynomials. Now, when we talk about polynomials, we classify them in a couple different ways. If you look on this same page in the textbook, we define some terms. Just below the brown box, second sentence, referring to the polynomial she has written above, it says, this polynomial is written in descending powers of the variable, because the exponents on x decrease from left to right. My first polynomial is in descending powers, because from left to right my powers get smaller. This second polynomial is not, because my powers go from x to the 5th and then jump up to x to the 8th. This is not in descending powers. If I were asked to write this in descending powers, I would just reorder. Remember, addition is commutative. We can juggle addition. You can't juggle subtraction. And what else do we say? Signs belong to their terms. So to write this in descending powers, I would write negative 7x to the 8th and then plus that 6x to the 5th. That's the same expression, essentially, but now it's in descending powers of the variable. At the bottom of this page, we define the degree of a term and the degree of a polynomial. It says the degree of a term is the sum of the exponents on the variables. It goes on to say the degree of a polynomial is the greatest degree of any non-zero term of the polynomial. Well, a non-zero term just means you can see it. If it were a zero term, I mean, we have a plus 0x that we could write here without changing the value. We have a 0x to the 5th we could tack on the front without changing the value. That's what it means by we're looking at the non-zero terms. It's the ones that you can see. Okay, so let's take a minute and just talk about the degree of a term. Here's the term, and I want to know its degree. The degree of a term is the sum of the exponents on the variables. So the degree of x to the 4th is that 4. The degree of a squared b cubed, that's a single term. And it says the term is the sum of the exponents on the variables. 2 plus 3 is 5. If I have something like 7mn, What is the degree of this term? We're going to add up just the exponents. That 7 has nothing to do with the degree. What's the exponent on this m? If there's one factor of m, we understand that that is m to the first. Likewise, n to the first. And so the degree of this term is 2. The degree of just a numeric term, just a 6 by itself. Add up all of the exponents on all of the variables. Well, it's going to behave like this. We can think of this as having a variable part that's raised to the 0 power, which is why you can't see it. So a numeric term, if you think of it as being times some variable to a 0 power, well, then the degree of this term is 0. The degree of any numeric term, without that fraction part, the degree will be 0. Let's classify these polynomials as to their degree. The first polynomial. This first polynomial, it says the degree of a polynomial is the biggest degree of any term. So what do we have? We have our first term has degree 4, our second term has degree 3, and our third term has degree 2. Pick the biggest. The degree of this first polynomial is 4. What's the degree of this second polynomial? Well, the degree of the first term is 5, the degree of the second term is 8, the biggest is 8. Let me return this to its original state, because I want to get used to looking at it without grabbing the pink marker. What is the degree of this term, of this polynomial? Well, the degree of this first term, that's x to the first, so the degree of this first term is 1. Any numeric term, we figured out, has degree 0. What's the biggest? So this polynomial has degree 1, or is a first degree polynomial. My little single term here, the degree of that term is 2. It's the only term, so the degree of this polynomial is 2. A numeric term has degree 0. It's the only term here, so the polynomial has degree 0. On the next page, at the top, page 290, we learn to classify these polynomials as to their number of terms. And running through it quickly, we have that a monomial is a polynomial with just one term. Mono means one. A binomial is a polynomial with 2 terms, bi meaning 2. And a trinomial is a polynomial of 3 terms. Tri, of course, meaning 3. Anything bigger than that, we just say, oh, we've got a polynomial of 5 terms. There are no special names above trinomial. So let's classify these now as to their number of terms. This first polynomial has 3 terms, so it is a trinomial. In fact, we can say that this first polynomial is a trinomial of degree 4, or a 4th degree trinomial. My next guy has 2 terms, so he's a binomial. Third one down, also 2 terms, also a binomial. Next to last, we have a single term. One term is a monomial. Likewise, a single term here at the bottom, this is also a monomial. So now we can classify these polynomials as to their degree and as to their number of terms. Let's do one more. Those were all polynomials in X, or could be considered polynomials in X. Here's a polynomial. It's time to change out this black marker. I want to classify this polynomial in m and n. It's not a polynomial in x, it's a polynomial in m and n. I want to classify it as to its degree and as to its number of terms. As far as the degree goes, I need to figure out the degree of each term. The degree of this first term, you add up the powers on the variables. 2 plus, what right here? A 1. 2 plus 1 is 3. This first term has degree 3. Second term has degree, well, that's m to the first, so 1 plus 4, that's degree 5. And my final term, 2 plus 2, it has degree 4. So what is the degree of this polynomial? Pick the biggest. This polynomial has degree 3. I'm sorry, degree 5. And now classify it as to its number of terms. Is it a monomial, binomial, trinomial, or none of these? 4 or more terms, I would say it's none of these. It's a polynomial of however many terms. But we see 3 terms here, so this, of course, is a trinomial. A trinomial of degree 5, or I might say a 5th degree trinomial. That's the tough part. We're done with the tough part of the section. The rest is going to be smooth sailing. Let's turn to the homework. And one of the first things that she does is, let's look at number 16. In number 16, she gives you a polynomial in V. And she asks you to determine the number of terms and name the coefficients of those terms. Well, how many terms are there? We see 3 terms. Terms are separated by pluses and minuses, unless those plus or minuses are buried under parentheses. There are 3 terms: the v, the minus 2v cubed, and the minus v to the 7th. 3 terms. She did not ask me to classify, but I know I could call that a trinomial. 3 terms. And then she said, give me the coefficients of those terms. The coefficient on the first term, what's out in front of this v? We can't see it, but we know there's a 1. The coefficient on this middle term, signs belong to their terms, so the coefficient is negative 2. The coefficient on this last term, you can't see the 1, but it's there, and signs belong to their terms. Coefficient on that last term is negative 1. In the next batch of problems, I'm going to grab number 26. The instructions say, in each polynomial, simplify by combining like terms whenever possible. And in exercises up through number 26, write the result in descending powers of the variable. So number 26, we're asked to simplify and write our final answer in descending powers of the variable. We have a couple of like terms. Remember, like terms match exactly in their variable parts, including the powers on those variables. Minus 3 plus 4, same as saying 4 minus 3, is 1. 1a to the 8th. We don't write the 1. And this other term is all by himself, this minus 3a squared. We've combined like terms. Now make sure it's in descending powers. Do the powers get smaller as I go left to right? Yes, they do. And so that's what we're after right there. Let's look at number 32. In number 32, we have some fraction coefficients. Fractions are real numbers. Any number on the number line is a real number. So this is still a polynomial. We've been asked to simplify this polynomial by combining like terms. Well, these are all like terms. These are all p squared q terms. Now, please understand, if I ask you to simplify 5p squared q plus 6p squared q, combine like terms, 11p squared q. If I had 2mn plus 3nm, we know multiplication is commutative, so mn and nm are the same. We can combine these like terms. But very careful. If I have something like 7a squared b plus 8ab squared, and I say simplify, well, these are unlike terms. That's an a squared, that's just an a. That's just a b, that's a b squared. These don't match in the variable parts, including the powers on each variable. These are unlike terms, and so this expression is already simplified. Be very careful with that. We've been asked to simplify here in number 32. These are all like terms, so I want to add them up. But I've got fractions, so I'm going to need common denominators. Least common denominator for 4, 3, 12, and 6 is 12. So what do I need? A factor of 3, top and bottom. Here I'll need a 4. This third one's good to go. And on the last one, multiply the top and bottom by 2. This gives me negative 9 twelfths p squared q minus 4 twelfths p squared q plus, this one was already ready to go with its twelfths, plus 7 twelfths p squared q and minus 2 twelfths p squared q. Add them up. I've got minus 9 of them, minus 4 of them, plus 7 of them, minus 2 of them. That totals what? Let me see. Minus 9 minus 4 is minus 13. I'm going to grab this at the end. I've got a minus 13, minus 2 is minus 15. A minus 15 plus a positive 7, that's going to be a minus 8 of them. Minus 9 minus 4 plus 7 minus 2 totals minus 8. Minus 8 what? Minus 8 twelfths p squared q. And of course this is not simplified until I make sure that my fraction is reduced to lowest terms by a factor of 4. That reduces to a negative 2/3 p squared q. While we're at it, go ahead and classify that as to its degree and its number of terms. The degree of this polynomial, add up the powers on the variables. That's p to the second and q to what? Q to the first. 2 plus 1 is 3. This polynomial has degree 3. And what kind of omial is it? There's one term, so this is a monomial. If you were asked. If you were asked. Look at number 36. In number 36, the instructions. For each polynomial, first simplify if possible. Write the result in descending powers of the variable. Then give the degree and tell me what kind of omial it is, right? Tell me if it's a monomial, binomial, trinomial, or none of those. We don't want to classify a polynomial until it is simplified. Initially, we have 4 terms here. Does that make this a polynomial of 4 terms? I need to see it simplified before I can think about that. So if possible, we want to simplify. Well, we do have like terms. And we want this simplified answer in descending powers. I'm going to work on that as we go. What is the highest power on p that we see? P to the fifth. So let's go ahead and get our p to the fifth term. 6 of them minus 8 of them is minus 2p to the fifth. What is the next biggest power on the variable p? P to the third. He doesn't match up with anybody else, so plus 4p to the third, and that leaves finally that plus 10p squared. Double check. Is this in descending powers of the variable? Do the variables get smaller and smaller as I go from left to right? Yes, they do. And so we've simplified. We want to indicate the degree of this term of this polynomial. The degree of this polynomial will be the biggest degree of any of the terms. This one's pretty clear. The degree of the first term is 5, degree of the second term is 3, degree of the last term is 2. The biggest of those is 5. So this polynomial is of degree 5. And it wants me to classify it as to its number of terms. We see 3 terms. This is a trinomial. She's going to have you plugging in to polynomials, which is something you can be expected to do in an algebra class. And next semester, it will probably be even more important as you start graphing these polynomial expressions, which will turn those into functions to be able to graph them. Number 44. Find the value of this polynomial given values for the variable. On a quiz or a test, I will simply say evaluate. Evaluate this polynomial given, and here in part A, we are given that x is 2. Evaluate this polynomial given that x is 2. Well, plug in. Plug in 2 for x. X squared, that's going to be 2 squared plus 5 times x, x is 2, and minus 10. And crank it out, order of operations. We'll take care of that power. 2 squared is 4. The very next thing I would do is this multiplication, so I'm going to go ahead and grab it in this same step. It's unrelated, it is independent from that first term. It's not waiting on the result of that first term, so I know I can do it in this same step. And minus that 10 at the end. Well, 10 minus 10, those are gone. The answer is 4. Or if you want to go left to right, 4 plus 10 is 14, minus 10, you're back to 4. Let's do part B. Same problem, but this time, let x equal negative 1. When x is negative 1, now think about this. This is going to trip a lot of people up if they're not paying attention. What's being squared in my polynomial? That x. I'm replacing x with negative 1. What needs to be squared? That negative 1 that's replacing the x. Is that what I've written? No. That negative is floating, isn't it? It's not part of the base. If I'm going to plug in negative 1 for x, then that negative 1 needs to be in parentheses, so the whole negative 1 that I'm plugging in is getting squared. We're squaring the negative 1 plus 5 times negative 1 and minus 10. Negative 1 squared, negative 1 times itself is positive 1. 5 times negative 1 is minus 5, minus that 10 at the end. And from left to right, 1 minus 5 is negative 4. Minus 10 more drops me down to negative 14. The thing that I want you to pay attention to here is when you're plugging in these negatives, if they're the base of some power, This was x squared. What's x going to be? -1. So you better be squaring the whole -1. That -1 needs to be in parentheses. All right. When I mentioned the title of this section, I said we're going to be adding and subtracting polynomials. We have yet to do that. Let's have a look at number 66. In number 66, my instructions might say simplify, or they might say add. Now we're adding these two trinomials. And I really don't think you need much coaching on this. Because if I'm going to simplify this expression, what am I going to do? Well, chapter 1 says to simplify means to have, we already knew that we had to have our fractions in lowest terms. It also means to remove grouping symbols and to perform all operations that are possible, including combining like terms. So what can you tell me about adding these two polynomials together? Well, let's remove the grouping symbols. I can drop the first set of parentheses because there's no number, no negative to distribute. Associative property of addition says I can group addition however I want. Nothing to distribute, I can drop that first set of parentheses right away. My second set of parentheses also falls right off because I'm adding, and addition is associative. Again, in other words, there's no number, no negative that needs to be distributed into the parentheses. So those fall right off. Now it's a matter of combining like terms. We've got some b to the sixths. Minus 2 of them plus 1 of them is minus 1 b to the sixth. We don't write the 1. We've got some b to the fourths. 3 of them plus 2 of them is plus 5 of them. And we've got some b squareds. Remember, signs belong to their terms. So this is a minus 1b squared plus 2b squared. Well, that's the same as 2 minus 1 is 1b squared. We don't write the 1. And this is simplified. We just added two trinomials together. Let's look and see what she has to say back in the section when it comes to adding polynomials. Here at the top of page 291 in the blue box. This is one of the easiest blue boxes we've got. It says to add two polynomials, add like terms. That's what we just did. And it made perfect sense to us. If we're going to simplify that, drop the grouping symbols, which we could because addition is associative, and add them up, combine like terms. Well, what does she say when it comes to subtracting polynomials? This one's a bit verbose, a bit wordy. Page 292 at the top, subtracting polynomials. It says to subtract two polynomials, change all of the signs of the subtrahend and add the result to the minuend. Okay. First of all, just watch this. If I say 5 minus 3 equals 2, we know that 2 is called the difference. What are the members of subtraction? I mean, when we do a division, we know that 10 divided by 2 is 5. 5 is the quotient. 10 is the dividend. 2 is the divisor. What are the names of these guys? Well, she reminds us here in the blue box. The first term is called the minuend, and the second term is called the subtrahend. So, all this boils down to, she says, change all the signs of the subtrahend. That's the second polynomial. Guys, all that means is distribute the negative. Distribute the negative. I think we could have worked this problem. I'm going to back up and grab number 64 now. I think we could have done this problem without reading her blue box, because it just makes sense. We want to subtract. Here in number 64, subtract this binomial minus this trinomial. If I think of it just in terms of simplifying, what am I going to do? First, I need to drop the grouping symbols, and then I need to combine like terms. I can drop the first set of grouping symbols immediately because there's nothing to distribute. Associative property of addition says I can drop those parentheses. I can drop the second set of parentheses after what? After I distribute this negative. That will change the sign on each term in my trinomial. We now have minus 3x squared minus 2x plus 1. So what did we just do? We just changed the signs on all of the terms of my subtrahend. Whoopee. We distributed a negative. Simple enough. And then combine like terms. We've got some x squareds. One of them minus 3 of them, because signs belong to their terms, is minus 2x squared. I've got a couple of linear x terms. Linear means raised to the first power. One of them minus 2 of them. Leaves me minus 1 of them. Minus x. We don't write the 1. And this guy here at the end, he's all by himself. Plus 1. So to add or subtract polynomials, remove the grouping symbols and combine like terms. If there's no number or negative to distribute, the grouping symbols fall right off. If you have a number, or here a negative, you distribute that negative or that number in order to be able to remove those grouping symbols. Nothing really new about that. We were doing that back at the end of chapter 1. We just didn't call things polynomials. And here again, this is one of my favorite kinds of problems. Let's see if we can get this right, because we kind of blew this. A lot of us did on this last test. Number 68. It says, subtract this from that. I like this problem. This is a good problem. If I say subtract this from that, I am subtracting that minus this. I am subtracting this second trinomial minus that first trinomial. Note the parentheses. You're subtracting the whole thing. That negative will need to be distributed. Subtract this from that. We write that minus this. The whole thing. That whole thing minus this whole thing. The parentheses. Now we do what we just did a moment ago. Drop the parentheses. First set's gone. There's no number. There's no negative to distribute. And after distributing this negative into my second trinomial, I can drop the second set of parentheses. We now have minus 19 t to the fifth plus 6t cubed and minus t. Combine like terms. Minus 11t to the fifth plus 9t cubed 5 minus 1, that's going to be plus 4t. Subtract this from that. I like this problem. A lot of us messed up this kind of problem on test 1. So I will probably give you another opportunity to show me that you can do a problem like this. Subtract this from that. We'll finish up with a geometry problem, number 84. In number 84, we're asked to find a polynomial that represents the perimeter of the shape. This is a rectangle, and it is labeled that one of its sides, we'll probably call this the length. Although length and width are interchangeable, length does not necessarily mean the longer one. And we label this side, which we will probably end up calling the width. So we have our rectangle, and we want to find the perimeter. Well, I know that the perimeter of a rectangle is 2 lengths plus 2 widths, which is really just what? Adding up all 4 sides. And you could do it that way. The trinomial plus the binomial plus the trinomial plus the binomial, combine like terms. Or we can use our formula, which is just basically going to add up the 4 sides for me. So my perimeter is going to be 2 times, we'll call that top one the length, plus 2 times this other one we're calling the width. And now simplify. Well, I need to drop these grouping symbols. To remove the first set of parentheses, I'll distribute this 2. So that gives me 10y squared plus 6y plus 16. To drop the second set of parentheses, I'll distribute that 2. Plus 2y and plus 8. And then to finish off, we'll combine like terms. The y squared, this 10y squared is all by himself. We've got a couple of y terms that total plus 8y. We've got a couple of numeric terms. 16 plus 8 gives me plus 24. This is the perimeter of that rectangle. Very straightforward. This is a nice, direct kind of section to work on. Perhaps the easiest section that we've worked for quite some time now. Because what did we do? We had 2.5, some geometry word problems, 2.6, ratios and proportions, 2.8, inequalities. All of chapter 3, we had linear equations where we're graphing lines, getting slopes and intercepts, finding equations of lines. The first 2 sections in chapter 4, we're learning all these rules of exponents. It's kind of nice to have a section here that gives us a little bit of a break. If we can combine like terms, if we can distribute, if we know how to simplify, we pretty much got it made. So that's section 4.4. I'll let you get to that homework.